Okay, today we're going to take an extension of 9.3 and take it that one more step further today and talk about linear programming. Reading things on page 664 in your text could be extremely helpful to you looking at the vocabulary that we're here. We're going to be doing what we did yesterday, creating that feasible region where all the possible answers are at. And we're going to find our vertices. We're going to find all intersection points. So your intersection points will be ordered pairs, and you'll kind of list all of those intersection points as ordered pairs this way. Once you have those intersection points, what you're going to be doing is you're going to be plugging them in. Plug them in your objective function. What are we trying to maximize? What are we trying to minimize? We're going to plug it into our objective function. And the objective function is demonstrated by the equation C equals, it's usually in standard form, an AX plus BY situation. Your constraints, this is what we've already been graphing. These are our linear inequalities. The first few that we're going to do, we're going to be talking about, we'll be giving you the constraints and giving you this information as we go through. So if you turn to your first one that you've got, okay, there's some more description at the top to help you out a little bit there. But if you look at where it starts to talk about solve for the minimum value, that minimum value obtained from the objective function, C equals 2x plus 6y. Notice this is in standard form. This is the objective function. This is where we're going to plug things into at the end. We are given all of our constraints. There are 4 constraints that we've got, and we're going to graph all these constraints, noticing that the bottom 2 inequalities give us values in quadrant 1. I talked about this with your graph paper yesterday. Quadrant 1, so if you don't want the axis system, just draw quadrant 1 on your paper. We're bounded here by our x and our y axis. If we look at solving our other equations here, this is going to get us to an equation, a constraint that talks about solving for y if you want to. Y is greater than or equal to that negative 2/3 x plus 4. We can graph that. You can also graph using our intercepts. Intercepts with the cover-up method. If x is 0, you get a y value of 4. And if y is 0, you get an x value of 6. Plotting those 2 points over 0 and up 4 gets us that equation without having to worry about that slope. I plot 6, 0, and I'm going to draw my line as straight as possible. Okay, get your straight edge out, make sure it's going to hit right in the corners that you have, okay, taking care that it's the right way. Now we're going to graph, it says graph above that line, so we're shading in this direction. The second line we want to graph then, or that last one that we have left to graph, is this one here. Once again, I'm going to graph using my intercepts. If x is 0, then y is going to be 3. And if y is 0, then my x is going to be 9. Using your intercepts gets you really good points without having to put a lot of ordered pairs plots as you go through. So over 0 and up 3, and I'm going to go over 9 and up 0. And once again, I want my line as straight as possible, so that it's as accurate as can be. Now, for this particular one, I still want to be above because it is a greater than symbol. I still want to be above that line, and that y value was not negative. So I'm above this line and I'm above this line. So all of my feasible region, denoted as the capital letter R, is in the shaded region here. Our points of interest as we continue on with this particular problem is we now want to do what we call maximize it or minimize. We want to find our minimum value that works for our constraint. So we're looking at the region, and I want vertices of the region. Here's one of the vertices here. We know what that ordered pair is. That ordered pair is 0, 4. Another vertice of the region is right here, and another vertice of the region is right here. We know this one as well. That was over 9 and up 0. So I have, of my vertices, I have 9, 0, and I have 0, 4. And my other intersection point that I have is going to be in this spot here. We just have to figure out, is this, what is that intersection point? So we want to find out where these two equations intersect. If it's not clear on your graph, which my graph was off a little, so it's not a clear intersection point, I'm going to multiply that second equation by -2, greater than or equal to -18. We're just going to make them equations at this point and solve. -3y gets us to -6. So y is at 2. If I plug things back in and y is 2, then my other intersection point, y is 2, I'm going to find that my x value, plugging it back in, I get 3. So my intersection points I have identified. I have 0, 4, I have 3, 2, and I have 9, 0. There are my vertices. We want to check each of those into our constraint and see which one gives us the minimum value. So as we look at things, our constraint, we have the equation c equals 2x plus 6y. We're going to plug each ordered pair into that particular value. I plug in my x, I get c equals 2 times 0 plus 6 times 4. So when I plug in 0, 4, we get a value of 24. When we plug in 3, 2, I have 2 times 3 plus 6 times 2. When we solve that, I get 6 plus 18. 6 plus 18 is also, or sorry, 6 plus 12 is 18. That was a step ahead. The last one, we're plugging it back into our constraint, our C equation. I have 2 times 9 plus 6 times 0. This also gives me a value of 18. So when I look at this, I'm looking for a minimum, because that's what was described to us, was a minimum value. Minimum values happen at 2 places. Okay. So how we're going to state this is that our minimum, if this was a cost, go back up to the top. Does it talk about what situation we're discussing? No, but let's say it was a cost. If it was a minimum cost, we'd say our minimum cost is $18. And that this happens when three of x and 2 of y and 9 of x and 0 of y are produced. Okay. So when you look at where 3, 2 and 9, 0 are at, anything on the line that connects them will also work and achieve our minimum value. Anything on the line connecting our minimum values will also achieve your minimum value. So for your first couple, as we're going through on your assignment, you're going to be given your inequalities, you're going to be given your constraint, you're graphing your feasible region, you're identifying your vertices, you're plugging those vertices into your constraint and finding whether it's the minimum value or the maximum value based on what we're looking for in the description of the problem. As you move ahead to the next slide, on page 665 in your book, it talks about the steps. It gives you all of this information. So make sure you read through some of this and see how things are going to work. And look at the examples that the book gives you as well. It talks about sketch your enclosed region. They call this region R. Okay. Find the vertices of R. So find the vertices of your feasible region. Calculate the value of the objective function C at each one of the vertices. Select the max or min amount of C based on that point. So in this next example, we talk about find the maximum value for C equals 7x plus 3y from the following. It gives us what our constraints are. Once again, we're bound by quadrant 1. So I'm looking just in this area, graphing my next equations that we have. I'm looking at intercepts. This problem right here is going to give me if x is 0, then I set it equal, I would get a value of 5 for my y. If y is 0, then I have a negative 10 value for my x. So even though I have a quadrant 2 point, my shaded region will be bounded into that quadrant 1 by the axis system that we have. So finishing up graphing this line, I go over 0 and up 5. I go back 10 and up 0. Evidently, I'm going to need to change things a little bit. Let's go by 2s. I'm not going to get to 10 on this axis system that I have. So I'm going to change my axis in both directions to go by 2s so that I can get to 10. Negative 2, 4, 6, 8. There's my negative 10. My 5 is going to be an approximate spot then as we go through 2, 4. It's going to go through my 5 that's here about right there. And if I go up another, my slope then for that particular problem, go up another 5 and over 10 to finish things up, get a straight line. Okay. And notice it's approximate in that spot. We might have to move that line just a little bit so that we are getting through the appropriate spot to where we need to go. Okay. Looking at that line for shading wise, I'm going to have to change the direction of my arrow. So I really want it becomes a less than or equal to because of that negative. So we're going to be shading underneath that line that's there. We're shading to the right of the x-axis and above the y-axis. That last problem, that last inequality down at the bottom, using my intercepts once again, if x is 0, y is 10, and if y is 0, x is 5. So going once again up to over to 5, 0, I'm right here in the middle. My 10, 0 is here, drawing a straight line as we connect them. Okay. So for this problem, I didn't change the direction of my arrow because it was a positive y value. So I'm still going to shade underneath that. So we're shading underneath here, underneath here. So all of our answers happen in this shaded region inside, bounded by the x and y axis. That's what's called our feasible region. Once the feasible region is done, we want to identify our vertices on that region. So I have a vertice at 0, 0. Minimums will usually occur here, if that's the possibility. I have a vertice here. We knew when we graphed that one that that was 5, 0. We have a vertice here. We also know when we graphed that one, that was at 0, 5. So the one that remains needing to be found is this one right here. And if you're graphing very easily and carefully, you're going to notice that that actually crosses at 2, 6 very nicely. If your graph isn't showing a nice thing, we need to solve where these two equations right here are going to intersect. So we would have x minus 2y equals negative 10. 2x plus y equals positive 10. Multiplying this top equation by negative 2, I get negative 2x plus 4y equals positive 20. Adding things together, I get 5y equals 30. So my y value is 6. Plugging that back in, I would plug it into this equation here. I would get 2x plus 6 equals 10. So we get that our x is 2. Okay. The more carefully you draw and pay attention to your scale, the less you're going to have to solve for the intersection points at that spot. Now, you're going to take your vertices and we're going to plug them into our constraint. Our constraint, sorry, not our constraint, our C equation, our objective function. In this particular case, we're talking about 7x plus 3y. Okay. When we plug each of the vertices in, we're looking for a maximum value that we have. I plug in 0, 0. So when I plug in 0, 0, we get 0 as our value. When we plug in the ordered pair of our vertices 5, 0, we get a value of 7 times 5 plus 3 times 0 gets us to 35. When we plug in 0, 5, I'm going to get 7 times 0 plus 3 times 5 gets us to 15. And the last one we need to check was our ordered pair 2, 6 at the intersection point that we had. Plugging in the 2 for x, I get 7 times 2 plus 3 times 6 gets us to 14 plus 18, which is 32. I look at all of those values. I have a value of 0, a value of 35, a value of 15, and a value of 32. For this problem, we're looking for the maximum value. Maximum value is 35. So the way we're going to summarize all the hard work you've just done is we're going to say our max value is 35, and it occurs at the ordered pair 5, 0. Now, when we get to the word problems, we need to make sure we put units on what that max value represents, put units on what the 5 is or the x value is and what the y value is. We will pause now, and you'll have to play the second video for the word problem example. I hope things are going well thus far. Make sure you refer back to your book.